Okay, so it's our pleasure today to have Marcel Franz joining us from University of British Columbia. Marcel has been doing a lot of work lately on many topics, ranging from how to see quantum gravity in the lab to phases of Majorana fermions in condensed matter systems. And today he'll be telling us about interesting physics that can be accessed by taking two-dimensional layers of a three-dimensional high TC superconductor. So Marcel, please take it away.
Yeah, thank you for your introduction. This is a kind of new topic for me. So this talk I'm giving maybe for the third time ever, after often talking about ADS-CFT type dualities and black holes in the lab and things like that. This is a kind of more traditional condensed matter topic where we asked the question: what happens when we put together two layers of a high TC superconductor with a twist? So it's a variant on twisted graphene paradigm, and there's some interesting results that I would like to share with you that come from this. So this work has been, there's contributions from a number of people from several groups. We have a nice collaboration with experimentalists in our institute, Andrea Damascelli's group and Ziliang Yi's group, and I will mention some of these ongoing efforts. But the bulk of the work that I'm going to discuss today has been done by these two characters, my two students, Oz Ken and Tarun Tumuru, who did most of the calculations. And we had support from Ryan's Day, who's nominally an experimentalist in Andrea Damascelli's group, but he's done some first principles DFT calculations that support some of our findings. So let me move straight to the basic idea that I'm gonna elaborate later on. Imagine you have a monolayer of a D-wave superconductor, such as bismuth 2212, which is the iconic high TC cuprate. And if we know anything for sure about these materials, then we know that they are D-wave superconductors. And this has been tested in many different experiments. So imagine you take one such layer, then you add another layer, and as with graphene, you assemble the two with a twist. And here I'm kind of considering a large twist, close to 45 degrees. When the two layers are coupled, namely you allow electrons to tunnel in between, you get a picture something like this. And when you stare at this picture for a moment, what it reminds, well, at least me, is this dx squared minus y squared plus I dxy superconductor, or D plus ID. And this has been considered in the literature in various contexts because this state, if present, is interesting. It's a spontaneously broken, fully gapped superconductor, which is also topological in that it has chiral edge modes associated with it. So, at this point, I'm just motivating what might happen, but as I'm gonna go through the talk, I will argue that this is actually energetically preferred state in two layers with a twist close to 45 degrees, and with it several levels of modeling to support this idea. And there's now experimental efforts in several labs that seek to establish whether this is actually true. So if correct, if this was this spontaneously T-broken D plus ID superconductor, then this would be the cartoon of the resulting material. It's a fully gapped superconductor in the bulk, and it would have these protected chiral edge modes. Now, this is not merely fantasy. As of last year, these monolayers of BISCO, high TC superconductor, actually exist and have been measured in this fantastic series of experiments by Yang-Bo Zhang's group, published in Nature 2019. And what's kind of fascinating about this, it's apparently been a long route towards exfoliating single layer high TC cuprate, and there's some tricks, just like with graphene, to make it work. But this group actually managed to make it work, and they showed that a single monolayer of this material actually superconducts at temperatures close to the bulk crystal temperatures. So it's not quite 90 Kelvin as the bulk crystal. This is the graph, but it's pretty close, within 2 Kelvin for a single monolayer at optimal doping. Moreover, these monolayers actually exhibit the same phenomenology as high TC cuprate. So for those of you who know the canonical high TC cuprate phase diagram, you recognize this superconducting dome, where as a function of doping, which is this parameter delta in the oxygen concentration, the TC reaches maximum at this optimal doping. And this is known in bulk crystals, where you have to elaborately grow each single crystal at each doping separately. In this monolayer, actually, this data is taken in a single monolayer where through annealing and oxygenation, they can change doping in that single monolayer. So they can map out considerable portion of this phase diagram. And importantly, it remains superconducting, and you can actually go back and forth and manipulate this monolayer. So what we're thinking about is taking two such monolayers and assembling them with a twist to see if we get this topological superconductor. So let me give you a brief reminder about this D-wave superconductivity. Standard dx squared minus y squared. The cartoon looks like this. The blue line is the Fermi surface, which I'm representing here as a circle for simplicity. And then the order parameter changes sign upon 90-degree rotation and has these point nodes at 45 degrees along the diagonals, which, in the vicinity of those, the quasi-particle dispersion is somewhat similar to graphene, although it's anisotropic, unlike graphene. Now, pure dxy would be obtained by simply rotating this picture by 45 degrees. So it has now maxima along the diagonals and minima along x and y direction. Now, if you were to combine the two order parameters with real coefficients, and you can easily do a simple calculation, all you would find is that the system remains gapless, but these nodes now detach from the diagonals, and depending on the coefficients, they can be anywhere. You can rotate this just like D-wave orbitals. However, as soon as you combine them with a complex coefficient, like in this case, then you immediately gap out the original nodes. And this is simply because you're adding the gap amplitude and quadrature when one is real, one is imaginary, and so the gap then never vanishes on the Fermi surface, and you get a fully gapped superconductor. Now, so this is the preview of some of the results. What we find through, again, various types of modeling is that if you assemble two such monolayers with a relatively small twist angle below certain critical angle, then you find a situation that is energetically preferred that is similar to this. There's no spontaneous time reversal symmetry breaking, and you simply get two Dirac nodes, each one coming from each layer if you zoom in on one of these regions. However, when your twist increases beyond certain critical value, which depends on details, then you go into this time reversal symmetry broken phase, and excitation spectrum near these nodes looks like this. So it's fully gapped.
Can I ask a question?
Sure.
Yeah, so gapped superconductor sounds like an oxymoron. Can you explain what you mean?
Gapped superconductor. Why does it sound like an oxymoron? So
if system is, for system to be a superconductor, I would expect there need to be some
Gapless excitation.
gapless excitations, yes.
No, so all standard BCS superconductors like lead, aluminum, and so on are fully gapped. And that's been showed early on. Basically, that's one of the key predictions of Bardeen-Cooper's Reaper theory, which was then verified by tunneling and other experiments that you take a metal like aluminum, it's gapless in its normal state. It has a Fermi surface, but then as electrons condense into a superconducting state, a gap opens up around the Fermi surface, and there is no gapless excitation. So, for instance, a superconductor cannot absorb any light with frequencies below the gap. That's been very well established. Now, high TC cuprates are an exception to this rule. In their native state, they are actually gapless. And that's this picture here, that the size of the gap on the Fermi surface actually has this D-wave structure, and it vanishes at 4 points. But, when I entered this field in late 90s, early 2000s as a graduate student and a postdoc, there's been huge fights about this among prominent people in the field, where there were shouting matches at APS March meeting. No, it's S-wave. No, it's gapless. It's D-wave. And eventually, of course, the field settled on this picture because the evidence became overwhelming. There's evidence for this gapless behavior from specific heat, from absorption experiments, penetration depth experiments, and so on. So these things are quite well established. And what I'm going to argue is that basically you can take this gapless D-wave high temperature superconductor, and by assembling it into a bilayer, you can actually create a special type of a topological superconductor that is fully gapped. So I hope that
yes, thank you.
The question. Okay, so as I mentioned, we went through several layers of modeling to prove this point and motivate experimentalists to actually try this in a lab. And I will briefly mention several of these pieces of evidence. And the easiest one is just to write down Ginzburg-Landau theory for this twisted bilayer. And as usual, what you do, you simply write all terms that are allowed by symmetries for the two complex order parameters that I call here psi1 and psi2. And to fourth order, these are all the terms that you can write down. The only kind of different feature here that follows from D-wave symmetry is that this coefficient B is dictated to the symmetry dictates that this coefficient B changes sign upon 90-degree rotation. And this is simply because these psi1 and psi2 are D-wave order parameters. They also have to change sign by 90-degree rotation. And so for this term to remain invariant, B also has to change sign. And so the simplest form that is consistent with this requirement is it's proportional to cosine to theta. There could be higher harmonics, but to leading order, where we just use this. Now, coefficients C and A are not really required by symmetry to change sign, so I will treat them as constants from now. So we can now solve this Ginzburg-Landau theory. And the only assumption that I'm making is that since the two layers are otherwise identical, the amplitude of the two order parameters has to be the same, this psi, which I take to be real, but they can differ in terms of there can be a relative phase in between them. Now I plug in this ansatz into the free energy and isolate terms that depend on this relative phase phi. And this comes from the last two terms, this B and C. And so this is the interesting part. So I'm interested in knowing what is the preferred, energetically preferred relative phase. this constant K here is simply this C divided by B naught. So it's basically a high school algebra exercise to minimize this free energy for various twist angles theta. And this is how it looks. For small twist angles, this cosine is close to 1, and the free energy is dominated by the first term. Typically, one expects this K to be a small number. However, as theta increases, this cosine becomes smaller and smaller, and there's a crossover to a behavior dominated by the second term. And you can see this crossover from blue curves, which have a minimum at 0, to red curves, which have 2 distinct minima at non-zero angles. And as soon as this happens, as soon as free energy develops these 2 distinct minima, the time reversal symmetry is spontaneously broken because you have 2 minima in free energy that are at different angles, and they correspond to 2 time reverse, 2 conjugate angles by time reversal. Now, you can extract the position of this minima as a function of twist angle, which is this red line here. So for small twist angles, the minimum is at 0, and beyond some critical angle that is close to 45 degrees or pi over 4, you have this non-zero twist angle. And so this region here, marked in red, is this time reversal symmetry broken, fully gapped superconductor, which is also topological, as I will argue in a moment.
Question?
One can add temperature.
Can I ask a question?
Yes?
Yeah, so can you say again what K, curly K is?
So this curly K is simply this this C coefficient divided by this B naught. So I've simply taken out this B naught coefficient so that I have prefactor unity here, and then what's left here is just the ratio of this.
And is it correct that your window, your topological window, is of order K, the size?
Yeah. So this K sets the size of this topological window. And of course, Ginzburg-Landau's theory alone doesn't tell you anything about how large this K is. And for this, we need some microscopic input. And I'm adjusting this K. It's about 0.1. And that corresponds to the parameters in microscopic theory, which lead to similar results. So there's already some input here. Note, however, that for arbitrarily small K, as long as it's non-zero, there will be some window of this behavior, although it may be very narrow. If this K is very small, then the window will be correspondingly narrow. Yeah. Now, also, because this is a competition between quadratic and quartic term in the free energy, this K will depend on temperature through its dependence on the order parameter psi. And that's how we can extract this phase diagram in the twist angle temperature space. And what you find is that there's this nice wedge of topological superconductivity, which kind of decreases at higher temperature. The range is smaller. However, interestingly, when you're exactly at 45 degrees, this topological phase extends all the way to 1 in these units, which is native temperature of the monolayer, and this can be 88 Kelvin, right? And that's why in the title, I use high temperature topological superconductivity at 45 degrees with some optimism. This could happen above liquid nitrogen temperature. So so that's Ginzburg-Landau's theory. One can go and model this using a very simple microscopic model. And this is just a continuum of Bogolyubov-Dejean, or you can think about this as a version of BCS theory of superconductivity. And this is the simplest model that one can actually solve by hand. So I'm using this simplest model for a D-wave superconductor with a simple circular Fermi surface and a canonical D-wave gap, and I'm simply modeling the twist by rotating the two D-wave gaps with respect to one another by this angle theta. And then, this is the Hamiltonian that I have to solve, and it turns out to just be diagonalization of a 4x4 matrix, which I can do, as I said, by hand. And again, I can minimize the corresponding free energy with respect to the angle, with respect to the phase between the two order parameters. And the result of that minimization now for kind of parameters that should be relevant to, say, BISCO, I find these blue lines, these blue dots. So again, at small angles, twist angles, the time reversal symmetry is unbroken, and then there is this crossover region where the time reversal symmetry is broken. Of course, the agreement between the Ginzburg-Landau, which is the red line, and the blue dots is, it's not an accident. I have adjusted the coefficient in the Ginzburg-Landau theory, this curly K, for this to exactly happen, but I'm allowed to do that because Ginzburg-Landau theory really doesn't constrain that coefficient. Now, what this microscopic theory allows us to do is also to extract this minimum gap. As I mentioned, this state is fully gapped, and so I can extract that as a minimum excitation value, and these orange dots represent that. In this simple model, this minimum gap can be quite large. It reaches 20 MeV at this 45-degree angle, and this is a healthy fraction of the full gap in BISCO, which is roughly 45 MeV, and that's an input into the theory. So this delta maximum gap is about 45 MeV, so this is almost a half of that minimum gap. So this is not small. This should be visible through basically any spectroscopy, such as tunneling or angle resolved photo emission. This should be visible in specific heat, for instance, because it's a sizable gap. Okay, so I mentioned this is topological superconductivity. How do we know this? Well, there's quite a bit of literature, or you will find discussion of this D plus ID superconductor in several papers dating back to late 90s and early 2000s. People like Bob Laughlin and Ashwin Vishwanath and others actually considered this. The motivation was that perhaps this state occurs spontaneously in high TC cuprates under magnetic fields, which proved to be incorrect in the end, but they still worked out the theory behind this. And so we know from those calculations that this is a topological superconductor. And the manifestation of this is that when you put the system on a strip and you look at the edges, the bulk is gapped, but there are protected edge modes that span the gap and exist on the edges, and they are chiral, namely they are directed, the quasi-particles in those edge modes travel as indicated by these arrows. So just to confirm that our model has the right ingredients to show this, we put it on the lattice. We choose a commensurate twist such that there is a relatively small unit cell, and we can actually solve everything now numerically, because it's no longer just 4x4 matrix. These are 20x20 matrices, but we can easily diagonalize them numerically. And what I'm showing you here is the spectral function of this system on a strip evaluated at this edge. So what you can see here is a bulk gap, this region around zero energy, that's the bulk gap. And you can clearly see these chiral edge modes that are unidirectional. There's 4 of them, which is again in agreement with these old calculations. D plus ID single layer superconductor is predicted to have a Chern number 2. Now we have 2 layers, so that gives us Chern number 4, and therefore we expect 4 edge modes, and this is indeed the case. Of course, the full spectrum would have a counter-propagating modes, but they are located at the other side of the system. That's the meaning of chiral edge mode. So, you know, just not that we didn't believe these old calculations, but it's satisfying to see that those edge modes are actually there and that we're not making any mistake. So our last level of modeling is kind of fully self-consistent calculation on the lattice. And this includes we do this because we can now include all the details of the Fermi surface of BISCO, which are fairly well known, and we can be more quantitative, and we can predict various quantitative aspects of this that experimentalists want to know before they start doing these experiments. So what we start from is a Hubbard model with attractive nearest neighbor interactions, and this is known for a single layer to produce reliable D-wave superconductivity. This is a kind of standard model that people use when they want to model D-wave superconductors in various situations. Of course, it avoids the kind of unresolved question, where does this attraction between electrons come from? We don't want to really get into that discussion, but this is a very simple model that gives a D-wave superconductor on the lattice if you simply assume that there is an attractive interaction and it exists between electrons on nearest neighbor sites. And we just apply this model for this double layer structure with some tunneling between the 2 layers given by this G matrix element. And I will comment on that in a moment. So as I mentioned, in order to get a crystal, we need to choose a commensurate twist angle. And for a square lattice, the set of commensurate twist angles is given by this simple formula where m and n are integers such as m is less than n. So for any 2 such integers, you get an angle, and at that angle, you'll get a commensurate, you get a periodic structure. And these are some examples of these periodic structures that you get, these moire patterns. So we are interested in angles approaching 45 degrees. The easy one is this one, where the 2 integers are 1 and 2. This gives a unit cell with only 10 atoms, and the angle is 53 degrees, which is reasonably close to 45. It already shows interesting physics. If we want to approach closer, we have to go to a unit cell that has 64. And then if we want to be even closer, we have to go to a really large unit cell. We can do all this numerically, although this last one takes many cores and a lot of time to compute self-consistently. As I mentioned, this model allows us to consider details of the Fermi surface, for instance, of BISCO, which are very well known from experiments and first principles calculation. So this is an untwisted bilayer. This is how the Fermi surface looks like. It's parameterized by these TIJs. And once we start twisting, the 2 layers are coupled, we get these interesting Fermi surfaces that deform as shown here. But again, this should be fairly realistic compared to the actual materials.
Marcel, I have a question. What is the doping actually? What is the filling factor in?
What is doping? I will comment on that.
Not the doping, but filling factor in bilayer graphene.
So, so I on this slide, I'm gonna talk about doping, and you can ask me a question again if that doesn't answer your question. Is that reasonable? So, so we do these calculations, and
let me just. I'm sorry. when you write Hubbard model,
Yes.
the previous slide, this model doesn't actually carry information unless you specify the doping or filling. Without filling, these two lines don't mean much, right?
So filling is
how
controlled
many
by
question, how many electrons per site?
Okay. So this is controlled by this parameter mu.
No.
And
in material, in real material.
And so half filling means that you would have 1 electron per site. At half filling, these cuprates do not superconduct. They are rather antiferromagnetic insulators. So you have to remove some electrons, which is called hole doping. And then beyond some critical doping, they start to superconduct. And this is controlled by this chemical potential mu. And what you have as a function of doping is the superconducting dome that I showed in my third slide. So in our calculations, we consider a range of these values mu that correspond to the values of doping that will give us superconductivity in this model.
But in real materials, is there any idea what doping is? What the doping is?
Yeah. So I can go to this slide again. And this is the doping axis, right? 0 here means half filling, and there's no superconductivity at half filling. Instead, it's an antiferromagnetic insulator, and at around 0.02 in these units, which is this parameter delta here, which is the doping, it starts superconduct, and the optimally doped situation is around this doping 0.17 or something. So that's
is this in real in bilayer graphene?
This is not bilayer graphene. This is bilayer bisco.
And we are talking about bilayer graphene or bilayer bisco?
No, I'm talking about bilayer bisco. Bilayer high TC superconductor.
Okay, got it.
Okay, so here's some results of this calculation of fully commensurate lattice model. And what we extract from these calculations is these phase diagrams. So let me walk you through these phase diagrams. On the horizontal axis is the chemical potential, which is the parameter that controls doping. Okay, optimal doping, which is a doping that maximizes critical temperature, is at about 1.3 in these units. So in the middle of the horizontal axis, this is where the critical temperature would be maximized. The vertical axis is the parameter that controls the tunneling between layers. It's the interlayer hopping amplitude. And the reason why we consider the whole range of these parameters is that it turns out, surprisingly, after almost 30 years of research on these materials, there's no consensus what actually these values are. Or in other words, if you go to the literature and you try to find what this number is, you find a range of numbers, which is roughly this range between 15 all the way up to 70 MeV. And this is just a testament to the complexity of these materials and to various disagreements that methods that are used to extract these parameters are encountering. So what we said is, okay, we don't want to commit to any particular value. We just calculate phase diagrams for this whole range of values and show that over most of the range of these plausible values, we get interesting physics from these models. So what's inside this diagram, the size of these dots corresponds to the size of this minimum gap, this topological gap that is induced due to the twist. And the color codes for the Chern number. Blue is Chern number 0, green is Chern number 2, and red is Chern number 4. So anytime there's a large dot, this is a time reversal symmetry broken phase, which is interesting, but only green and red are topologically non-trivial. Blue are topologically trivial. So this is a new feature of this fully lattice model. We didn't see this, blue region previously in a continuum model. And this new feature comes because we have more complicated Fermi surfaces and so on. Now, the encouraging thing is that for this angle that is closest to 45 degrees, pretty much everywhere in this phase diagram, you encounter the symmetry broken, time reversal symmetry broken phase, right? We don't know what this G0 value is, but if it's, I don't know, 40 MeV, then, and we can adjust the chemical potential, then we are bound to land for some chemical potential in an interesting topological phase, for instance, this green phase. Or if it's very weak, then we land in this red phase at slightly higher doping. So this should be viewed as a reasonably encouraging result, pretty much close to 45 degrees, pretty much everywhere in the phase diagram. We have something interesting to look forward to. We were surprised that we saw this green phase, which is Chern number 2. And at first we didn't understand this. Later we kind of realized this is actually a quite simple physics. So it occurs when interlayer coupling is strong or the chemical potential is quite low. And what's happening here is basically indicated in this cartoon. You have two bands from two layers, right? And they are split by some constant amount, which is proportional to this interlayer coupling, G0. And when that G0, so, okay, and then there's chemical potential, right? Normally, the chemical potential intersects both bands. And so you have two Fermi surfaces, which means that effectively you have two layers, each contributes Chern number 2, so you get this phase with Chern number 4 for two layers. However, if the chemical potential happens to drop below the bottom of this top band, you suddenly have only a single Fermi surface, and the system effectively looks like a single layer material. The other states have been depopulated, so they do not contribute to the Chern number, and that's this green phase with Chern number 2. Now, we also understand this blue phase in a similar way. It's basically a D plus IS phase, where, and it always occurs at this phase transition between the two topological phases, and there is a hand-waving argument which gives some intuition for why that happens, and I'll be happy to go through it if anybody's interested, but in the interest of time, I will move on. So the bottom line is that this detailed modeling shows that close to 45-degree twist angle, almost the whole phase diagram is interesting in that if you have the ability to control the doping level, which has been already demonstrated for a single monolayer, you should be able to find a interesting topological phase in this system. Okay, so the lattice model, again, just for completeness, what I'm showing you here is the spectrum calculated for the strip geometry in Chern number 2 phase. There's two edge modes in Chern number 4 phase. There's 4 of them, again, as you would expect. This is our prediction for tunneling spectroscopy. One thing that we noticed is that for Chern number 4 phase, the minimum gap is quite small, but still visible. It's few MeV, that's this bottom here, should be still observable through high resolution tunneling experiment. It's much larger in Chern number equals 2 phase, presumably because the Fermi surface then is simpler and the gap is not as much frustrated due to the presence of two complicated Fermi surfaces. And in this situation, the gap can be quite large, 15 MeV or so, and you know, it should be very easily observable in this situation by spectroscopies. Our collaborators performed density functional theory for this material. And our original goal was to get better handle on these parameters, especially for this interlayer coupling G0. In that we didn't quite succeed. And the reason simply is that these band structures look like this. They are very complicated. So this is for twisted bilayer. You have very many bands. And it is simply not easy to interpret what's going on and read off parameters of some simple tight binding model is just a very non-trivial issue. And this also should give you some flavor for why in the literature people don't agree on, even for untwisted structure, what this interlayer coupling might be. It's simply because these band structures look very much like this. And you know, depending on which feature of these band structures you look at, you simply arrive at different conclusions. However, what the upshot of these calculations, which was satisfying, was that they demonstrate the stability of this twisted bilayer, which was not completely clear to us whether, you know, these two layers would want to stick to one another in this twisted configuration. This clearly happens in these ab initio calculations. This is the total energy of the system as a function of distance between the copper oxygen planes. And there's a clear minimum which occurs at roughly 12.6 angstroms, which is very close to actually the bulk separation in an untwisted crystal. So these systems should be stable. And there is evidence that electrons tunnel between the two layers from the band structure. It's just difficult to extract specific values of this tunneling matrix element. Let me mention some experimental efforts. My colleague, Zili Yang at University of British Columbia in our institute has undertaken to make these twisted structures. And here's some first samples that he made. So basically the first success was his group was able to exfoliate single monolayers of visco material, and they demonstrated that they superconduct at high temperature. That's this graph. It's kind of unfortunate that these labels obscure the axis, but they get routinely superconductivity in the monolayer above 70 Kelvin, which is good. They also managed to fabricate twisted bilayers, but the question is what to probe, because the easiest thing, and this is what they do in graphene always, they look at transport, right? But transport in this sample will not really give you anything very interesting. It will just show you that the sample is superconducting. That it's a topological superconductor is harder to deduce from just IV characteristic, for instance. So what Zili Yang is gearing up to do, he's building an apparatus which will measure polar Kerr effect in these samples, which is an optical response, and it is sensitive to spontaneous time reversal symmetry breaking in the sample. So basically this is the sketch. You send in polarized light and you look for Kerr angle, which is the change in polarization angle. and you can relate this to anomalous Hall conductivity of that sample through well-known formulas that are in the literature. This can be calculated through standard methods of theoretical physics. And we've already performed such calculations. Let me just say that it seems like these twisted samples should give what one may call a giant Kerr effect, much larger than some other materials like strontium ruthenate, for instance, which have been proposed to be also spontaneously time reversal broken phases. And this is simply because all the energy scales in cuprates are much higher, much larger than in these other materials. For instance, the gap is about 2 orders of magnitude larger, and that translates to larger responses. So we are optimistic that this can be seen. So here's a comparison of our calculation here for this anomalous Hall conductivity compared to prediction for strontium ruthenate. You know, the shape of these functions is similar, but notice the scale. So there's 10 to minus 6 in strontium ruthenate, whereas there's 10 to minus 2, about 4 orders of magnitude in this structure that we're considering. So it should be much easier to observe if present this effect. I just learned about a month ago that Philip Kim at Harvard is doing experiments that are somewhat related to this. They don't have monolayers, but they have thin flakes that they assemble with twists. So these are thin flakes of the same material, visco. The thickness is about 10 to 20 monolayers, and they assemble them with various twist angles, and they measure basically Josephson current through this junction that is twisted, and they find some interesting signatures that I'm not allowed to show you because this is unpublished research, but we're working with them to see if they may have already some evidence for this spontaneous time reversal symmetry breaking. So do I have a few more minutes, or am I pretty much out of time?
You still have 10 minutes.
Okay, great. So let me now, this was about visco and high TC D-wave superconductors. Let me show 2 slides about a kind of variation on the same theme. And this is a similar construction for a P plus IP superconductor. And this is even more interesting because, so this is also a topological superconductor, but is in addition such that it has odd Chern number. It's predicted, P plus IP is predicted to have Chern number plus or minus 1. And as a result, it would have isolated Majorana 0 modes in a core of a vortex, for instance. Strontium ruthenate was thought to be a candidate for this type of a superconductor, but the most recent night shift data seem to preclude that possibility. It doesn't seem to be a P plus IP superconductor, so we're left basically with no candidate materials. So here's an idea how one can, in principle, engineer a P plus IP superconductor from a monolayer PX or PY superconductor. So let me show you a similar set of slides. Imagine you have a monolayer of a PX superconductor. You take another one and you assemble the two with now 90-degree twist. And what you end up with, again, is by the same mechanism, spontaneous time reversal symmetry breaking, and you would end up with a P plus IP superconductor. Now, the unfortunate thing is that in nature, we don't really have PX or PY superconductors as far as I know. So we thought of this artificial construction of such a monolayer. What we have is these 1D quantum wires that people investigate for Majorana fermion physics. And they are routinely constructed these days, and they can be assembled into various structures. This is maybe too optimistic, but basically, if you have an array of these one-dimensional quantum wires that are each of them one-dimensional p-wave superconductor, you can naturally couple them weakly and create a two-dimensional px superconductor, for instance, and then you can think of completing this construction. So this proposal is a little bit more far out there because this has not been really done, even the first step, but in principle, this is doable. So we've done some calculations. I apologize, I pressed the wrong button, so you have to see the animation again. So it's just one slide, results of these calculations for this type of double layer structure of model that describes this situation. And again, here's a similar phase diagram as before. It's a function of doping and an interlayer coupling G. And again, I just want to point out that there's a part of this phase diagram where it behaves effectively as this px plus IPY superconductor with Chern number 1 or -1. That's the orange and this dark green region. There's also topologically trivial regions and regions with some higher Chern numbers like +1, +2, and -2. And then there is the requisite edge modes. But the interesting phases are the Chern number 1 phases. And we tested that indeed, if one puts a system into, say, a Chern number 1 phase and models a vortex in the middle of such a system, then there is a Majorana zero mode associated with that vortex, as well as the companion zero mode that is at the edge, at the outer edge of the system. So this works as a theoretical construction. Certainly it works. If this might ever work as an experimental reality, that's a kind of big question mark, but it might be a route to this type of topological superconductivity. So this is my last slide. Just to summarize, we've exploited this twist angle engineering paradigm to propose novel topological superconductors. In the case of high TC cuprates, we're twisting two monolayer D-wave superconductors. And what we find is that when the twist angle is close to 45 degrees, then most of the phase diagram in these simple models shows interesting topological phases. The most interesting phase is spontaneously time reversal broken D plus ID superconductor, which has Chern number either 2 or 4, depending on parameters. These phases show protected Majorana edge modes and could be observed through spectroscopies or through T-breaking through probes that are sensitive to spontaneous time reversal symmetry breaking, such as a polar Kerr effect. And that's it. And I'd like to thank you for your attention.
All right, thanks a lot. Let's thank Marcel for the very nice talk. And we can take some questions. Yes, feel free to ask your questions. Kathy, you have a question.
Yeah, just clarifying, maybe the question really goes back to how in the world one layer BISCO is the same TC. You don't worry about BKT in any of this. This is all just what you call more strict mean field theory. So if in fact the one layer was a 90 degrees superconductor, then this would be half of that, or something. This transition would be half of it. You don't do anything more microscopic with the BKT physics in this story?
No, I don't. And you know, the nature, I mean, the experiment tells us that a single monolayer BISCO is an almost 90 degree superconductor. So that has to include all those thermal fluctuations calculations, right?
Mhm.
There's no way the material can evade that. Now, there's solid transport evidence for zero resistance state and tunneling evidence for a gap. So, I don't know what to say about that. I think what that tells us is that somehow the mean field critical temperature is higher than that, right? So that temperature measured by experiments is already renormalized by vortex, anti-vortex fluctuations. And yeah, so this is something that we don't really worry about in these calculations. And perhaps that's a next step, but we take as an input from experiment that these monolayers exist and that they superconduct, and we take it from there. Yeah, cuprates have many mysteries, right? We don't know really why they superconduct in the first place. And this is just another one of them.
And that the monolayer is exactly the bulk or near to the bulk is really pretty phenomenal without any BKT reference at all.
Yeah, when I saw those results, I literally kind of froze in place because, well, you remember this maybe better than I do. People endlessly argued over the years whether, superconductivity in cuprates is a property of a monolayer. And there's been some indications from, these films grown by Bozovic, for instance, and so on. But now this one cannot sweep this away by any arguments, right? This is just a freestand or monolayer on silicon dioxide, and they do transport measurement, and it shows zero resistance, right? So you can't just and it's now not just one lab. There are several labs that confirm that, including our QMI, where Ziliang has grown these or exfoliated these. He doesn't quite have 90-degree TC, but he has number of samples with TCs above 70 Kelvin. And he's been working on it for about a year now. So
Yeah.
It seems to be real.
Yeah.
Oh, you have a question?
Yes, I have a question and a comment. Let me start from the comment. Of course, you know, but didn't mention, probably forget to mention that helium-3A films is the example of what you call people SAP. It's also called chiral superconductivity, but that's an example, right? Which exists in nature. Of course, it's not. It's a very low CC superconductor, but that's a standard example, right?
Yeah, of course. I should have mentioned that. That's a well-known example that's been with us for many years.
Yes, but Mike, I have a question. When you model bilayers, I remember from one slide, you couple these layers. There is a coupling constant G, I remember.
Yes.
What is the model of coupling? Which G did you take?
Okay. So what we do, we use, again, the details of this interlayer coupling are poorly understood. We search literature, and there's a number of models which are different. So we tried several different things to show that our results are robust with respect to what we assume. And the simplest model that we use is coupling between sites, between layers, which decays exponentially with the actual geometric distance, with some length scale, which represents the extent of the active orbital. And that's a kind of reasonable model that people use in these bilayer calculations without a twist. Nobody has done twisted calculation. We used also a power law that doesn't change to things too much, we use the hard cutoff again. That seems to work as well. So,
but the coupling are all positive, right?
yes, these couplings are all positive. That is true. Yeah.
Okay.
Is the Kerr effect quantized?
No, this Kerr effect, we don't find it quantized. It actually depends on frequency and many other parameters. But you can show that it's quantized to 0 if time reversal symmetry is unbroken, or if you also have to break all mirror symmetries in plane. If there is any mirror plane left, then again it's quantized to 0. So you have to have sufficiently low symmetry in your system, which these twisted samples do have, because once you go to this D plus ID phase, then all mirror and of course time reversal are also broken.
What is the magnitude of the Kerr effect?
So we find it, again, depending on frequency, it's on the order of milliradians. And this is huge compared to what's predicted from strontium ruthenate, where it was nanoradians, right? So we believe that it should be relatively easily measurable. The difference in magnitude is basically because if you look at some simple estimates, they suggest that Kerr angle is proportional to the gap squared and superconducting gap squared. In high TC cuprates, the gap is about 2 orders of magnitude larger than in, say, strontium ruthenate. So that gives you 4 orders of magnitude roughly difference. And that's what we see in detailed calculations. So we tend to believe that's plausible.
Okay.
So the only thing that would be quantized here would be thermal Hall conductance. These edge modes, they carry a quantum of Hall conductance each, thermal Hall conductance. But in principle, this is measurable. But I'm being told that this is a very hard measurement. So we're trying to talk to some people who know how to do these measurements, but nobody is very enthusiastic about doing them.
I remember you said it's proportional to the quantum anomalous Hall coefficient. Is that quantized in some sense, or also not?
No, because so electrical. If you're asking about electrical quantum Hall effect, it's not quantized because charge is not a good quantum number in a superconductor. So that's the problem, and so you can calculate this sigma xy at finite frequency, sort of optical Hall conductivity, and you can show that it's 0 in a time reversal symmetry respecting phase and non-zero in the broken phase, but there's nothing quantized about it, just because basically because charge is not a good quantum number in a superconductor.
But is there a correlation between the sign of the Kerr effect and the sign of a churn number, or is there anything like that you measure which direction it rotates, and you can say?
We discussed that, and we're not entirely sure, but we believe there's a correlation between imaginary part of sigma xy and the sign of the churn number. So they should have the same sign. We cannot easily prove that, but our calculations show that effect. So we're still kind of debating whether this is an exact result or, yeah.
Mhm. Mhm. Thank you.
I guess ask a small question. What's the distance between the two visco layer in the exfoliated sample you show, like from UBC? Like the twist bilayer, like what's the typical distance?
Well, so we don't know that experimentally, right? According to our first principles calculations, it should be roughly 12.6 angstroms, which is the same as or very close to what it is in a bulk crystal. So that's what our DFT calculation shows. In actual experiment, right? They just assembled these recently. They showed they superconduct, but that's pretty much all that they've done so far.
Okay, thanks.
Any other questions? Actually, I had just a naive question about your, so in the first Landau-Ginzburg approach that you showed us, you excluded the possibility that one of the condensates goes away, say, so that there's a kind of symmetry breaking between the two layers. Is this, in the experiments, is it obvious that this is not energetically favorable?
Oh, okay, yeah, so we made an assumption that the two amplitudes are the same. So yeah, that excludes that possibility. I played with the free energy without that assumption, and I could never find any solution that would break that symmetry. So that, I guess that's all I can say. If, in other words, if you don't make that assumption, if you carry psi1 and psi2 as two different amplitudes, then all that you find is that the minimum occurs when they are the same. Yeah, and that seems kind of reasonable because, yeah, I don't expect the symmetry to be broken in that way between the two layers.